In objective 2 for this lesson, I'm going to use this thing called the location principle to try to figure out some zeros of some polynomial function. So in the picture here you see a sign that says change ahead, and it's a clever like visual pun. You're looking for a sign change. That's exactly what the location principle is based on, sign change. Don't believe me? Take a look. Okay, so take a look at that table of values that you see there. So I got my inputs x, my outputs f of x. We're going to use the location principle to just look at those numbers and go, oh, there's got to be a 0 between blah and blah. So I want you to just take a second and look at those table values and what can you conclude about the location of one of the zeros. Just go ahead and pause, give it some thought, and then come back. Okay, so you should have figured out that you have a 0 in between x equals 1 and x equals 2. Here's the reason why. I have my y value at negative 12, so think of on your graph you're down below the x-axis, and at the very next point I'm up here at positive 28. The only way to get from that bottom point to the top point is if you cross the x-axis in between those two. Okay, so take a look at it. This is that exact saying in math speak. So let's dissect this. Let's see what's going on. So if f is a function, a polynomial function, and a or b are any two real numbers, and I'm going to stick those two real numbers into the equation. So f of a turns out to be a negative number. F of a is less than 0. When I stick b in, f of b turns out to be a positive number, greater than 0. What that means is that you must have at least one 0 in between those 2 points. Right? So, for example, just looking at it in terms of having 2 points, if I plug in 2 in my function, I get negative 3. I plug in 3 into my function, I get positive 5. The location principle is saying that there's got to be at least one place where it crosses the x-axis in between x equals 2 and x equals 3. And this is because polynomials have nice, smooth, continuous curves, and in order to connect x equals 2 to x equals 3, it has to cross the x-axis to get to those y values. Here it is in a graph. We've seen this exact thing. Oh, why don't I animate that again? This is what we warmed up with. So here's the polynomial graph that connects these 2 points. And the only way that I can connect those 2 points, I have a negative 3 down here and I have a positive 5 up here. The only way that I can connect those with a polynomial graph is if I cross the x-axis between them. Okay, let me extend this a little bit further. What if I had picked instead, say, this point right over here? This y value is at negative 5. So if I knew the x value here, and maybe it's at 1, 2, 3.5, maybe it's at negative 3.5. I don't know exactly just yet. Okay, so if I take that initial point at negative 5 and this one over here at positive 5, the location principle is saying that even between these 2 points, since I'm going from a negative sign to a positive sign, I have to cross the x-axis at least once. And here's a case where it crosses not just once, but 1, 2, 3 times in order to finally get to that 5. All right? So with the location principle, oh wow, this thing is going to be animated one more time. It's what happens when you copy and paste. So basically, with the location principle, I'm usually given a table of values. And I'm looking to see where the y values change, the function values change from positive to negative or negative to positive. You're looking for a sign change. If it changes from positive to negative or negative to positive, there has to be a 0 in between those two x values. All right? So let's practice that right here. On exercise 9, here's my polynomial function. I give you a table of values. Now in the table of values, first of all, I've got 4 answers. That's what I should be looking for. And that'll make a lot more sense in the next lesson about the fundamental theorem of algebra. Okay, so before I look at the table of values, let's list out all the possible values that x could possibly be. So that's using the rational zero theorem. X could possibly be all the factors of 12, which are 1, 2, 3, 4, 6, and 12, divided by all the factors of 9, which are 1, 3, and 9. So divide those things out, the factors of 12 on top. So plus or minus 1, 2, 3, 4, 6, and 12. Now divide them all by 3s. So 1/3, 2/3. I don't have to divide the 3. 3 divided by 3 is 1. 4/3, 6/3 is 2, and 12/3 is 4. I already have it. And then divide them all by 9. So 1/9, 2/9, and 4/9. Okay, so that's a pretty big list. Maybe that location principle can help us narrow that down a little bit. So if I look at my table of values, I should notice that I have automatically a 0 right there at -2. Well, look at that. Part of your work's already done. Same thing right down here, scan right down here at 1. X equals 1. If I plug that in, I get 0 as my answer. So I could start with just one of those two, divide it out synthetically, and see what's left over. And then divide that answer by one of the other ones, and then I have a quadratic left over, and I try to factor or solve that some other kind of way. Okay, that would be the easy thing to do, and I'm not going to do the easy thing. The other thing I wanted to point out, so that we're actually looking at using the location principle, is look at these two values. I'm going from a 0, no, it's not those two values. Let me get that eraser there. I'm going from -18 all the way to +12. What that means is there has to be a 0 in between there. So 0 here. In between the two x values. So in between 0 and -1. If I look at my table, or if I look at my list of possibilities, what numbers are between 0 and -1? That could be the 1/3, and these are all going to be negative. 2/3, not the 4/3, because that's over 1. 1/9, 2/9, and 4/9. So just as an instance, like if I give you a table that has no zeros automatically and all it has is some sign changes, you still have to look back at that list and try to figure out which ones are going to work. So that's why I wanted to practice this with you. Otherwise, I could just use that -2, divide it out, use that 1, divide it out. Okay? All right, but look what happens. I've already done this for you because, well, just take a look. Whoa. So I tried to synthetically divide it by all 5 of those possibilities, the -1/3, -2/3, -1/9, -2/9, and -4/9, because those are all the numbers that are in between -1 and 0 that were in my list of possibilities. And you can see that not a single one of those worked. What does that mean? What it means is that the two that are in between there are one of two kinds. They must be either irrational or they must be imaginary. And in either one of those cases, I can only find them using the quadratic formula. So it was just kind of like a learning opportunity. So let's kind of clean the slate here and then go back to the same exact equation and go, hey, my teacher just helped me cheat just a little bit. Why don't I divide that one out? I know that one's going to work.
So by synthetic substitution, all right, 9, 3, -30, 6, and 12. 9, 9, 12, 12, -18, -18, -12, -12, and 0. All right, so there's the first one. Now I busted it down to a cubic. Here is another one that is already in the table. I'm going to divide that out of the answer. So -2, 9. 9 times -2 is -18, -6, +12, -6, +12, 0.
So what I have left over is this quadratic, 9x squared minus 6x minus 6. Let's make that equal to 0, because I'm going to simplify it just a little bit. Why don't I go ahead and divide everything by 3? So then I'd have a 3x squared minus 2x minus 2 equals 0. So based on what we saw, that scary piece of information back over here, I know that this thing cannot be factorable. I know that it must use the quadratic formula in order to solve it. So let's break that thing out. X is equal to negative b, so negative 2, so positive 2, plus or minus the square root of b squared, 4, minus 4 times a, 3, times c, negative 2, all over 2 times a, which is 6, 2 times 3. Okay, simplifying what's inside the parentheses here or underneath the square root. That's a negative 12 times negative 2 is positive 24, so I got 4 plus 24 is 28. X is equal to 2 plus or minus square root of 28 over 6. I think the square root of 28 simplifies. 28, 2 goes into that 14 times, and then 2 goes into that 7. Pair of 2's. So x is equal to 2 plus or minus 2 root 7 over 6. Hey, everything is even. Why don't I divide everything by 2? Finally, x is equal to 1 plus or minus square root 7 over 3. So there's our final answer. Those two plus x is equal to the 1 and the negative 2 that we found straight from the table. Now, there is something I do want to point out about those last two answers that we got from the quadratic formula. They are irrational conjugates. That's interesting. So why don't you go ahead and try some more of those exercises in the next video, and I'm going to wrap it up right here. So the rational zero theorem only helps in finding some zeros. It doesn't tell you which ones they are. So how do we go about finding the irrational ones? So it helps us find rational zeros, but it doesn't help us find irrational ones. How do we get the irrational ones, or even the imaginary ones? Just like we saw in the previous exercise, you have to use the quadratic formula. Or I guess you could complete the square. The last one, it would have been pretty messy to complete the square, so quadratic formula was the way to go. Okay. So that wraps up all of 5.6. Being able to use a graph to help us cheat, to help us find the approximate location of one of those zeros. Wherever it crosses the x-axis, that must be a zero. Divide it out synthetically. Location principle is very similar to this, but here we just might have a table of values and we're looking for where it changes. Look at the picture right there, from positive to negative. I don't know, what do you think? Is black the positive and white the negative? Whatever, you're looking for where it changes signs from positive to negative. In between those two, there must be a zero. So here is your assignment for this section. Which came first, the graph or the zeros? It's an interesting, deep philosophical question, Rowan. I don't have an answer for that one. So yeah, check out the exercise videos right below.